Okay. Ouais, il faut appuyer sur le micro. La cheville peut faire. Ça y est, ça le fait. Ah, oh. Donc, bonjour à tous. Donc, je m'appelle Igor Caron. Je suis un des co-organisateurs du Paris Machine Learning Monitor. Il y a dans la salle Jacqueline Fourien, qui est la deuxième organisatrice, et le fondateur se trouve où? Où es-tu, Franck? Ici, voilà. On co-organise ce soir le meet-up avec Women in Machine Learning and Data Science. Voilà, c'est un autre meet-up de qualité ici sur Paris. L'idée, c'est de faire en sorte que, des fois, on fait des choses un peu avec d'autres meet-up. Aujourd'hui, c'est le cas. Et pour la première fois, on fait un hors série avant le premier meet-up régulier. Donc, pour vous, et puis pour nous aussi. Notre prochain meet-up, c'est le 10 octobre, et ce sera à vente privée. Donc, ce sera très loin, mais en plus, on aura des choses super intéressantes, parce qu'on ira sûrement visiter l'intérieur de vente privée, donc il ne faut pas réellement louper ça. On l'a déjà fait il y a 2 ans, c'est absolument extraordinaire du point de vue data science, ce qu'ils font. C'est époustouflant. Enfin, moi, je m'étais pris une grosse claque la dernière fois.
Absolument, et aussi le côté découverte de vente privée, en fait, ils vont nous montrer leurs locaux, et il y a énormément d'œuvres d'art, et c'est de l'art moderne, et c'est vraiment, enfin, faut le voir pour le croire. Donc, venez le 10 octobre. Voilà.
Alors, deux autres petites choses. Une conférence qui s'appelle Hors série qui se passe le 17 et 18 octobre, donc on en reparlera dans notre newsletter. Et puis, il y a un autre meet-up qui est en train de se faire, qui est autour de tout ce qui est ordinateur quantique et tout ça. C'est aux alentours du 16 octobre, et ça se passera, je crois, chez WiMLDS. Maintenant, je me tais, et c'est à Caroline de parler de son meet-up et des invités.
Alors, moi, je suis très contente d'être là, à côté d'Igor, parce que si on s'est fondé, c'est grâce à une rencontre qu'il a indirectement organisée avec Chloé Agathe-Azenkotz, qui est une des fondatrices du Meetup. Et vous avez Chiara, une ancienne astrophysiciste, je vais la faire en français, une ancienne astrophysicienne qui s'est reconvertie en data science, et Marina. Nous, on existe depuis un tout petit peu plus d'1 an. Et on est hyper fiers parce que c'est la première fois qu'on fait un meet-up joint. Donc là, ce soir, vous aurez un speaker et une speakeuse. Notre prochain meet-up à nous, ce sera la semaine prochaine, mercredi prochain. Ce sera chez Blablacar. On aura la chance de recevoir Florence Dalchebuc, Gianni May, qui vient de Snips, et une troisième personne qui, elle, travaille plutôt dans la problématique business sur la Femtech. Donc ce soir, on est très contente d'accueillir Erin et Joe, que je ne vois plus, mais je l'ai vu tout à l'heure. Donc ils vont vous parler de ce qu'ils font en machine learning. Et là, je vais passer la main à Pascal. C'est ça, hein, Pascal. Stand-up pour Pascal, du groupe Inigma.
Merci beaucoup pour l'introduction. C'est un énorme plaisir de vous accueillir ici, sur un meet-up extra, et qui est au cœur de ce qu'on fait aussi sur un gymnase. Je profite de l'occasion pour vous raconter 2 secondes qui on est, et puis en quoi tout ça fait sens et à quel point c'est fait. Déjà, bienvenue. Un gymnase, c'est une société qui s'est construite il y a 4-5 ans sur une ambition qui était de faire de la R&D au service de plein d'autres gens, et avec une R&D externalisée, qu'elle soit en mission ou qu'elle soit en conseil, et au forfait et sur des projets sympas. Un gymnase, c'est un petit écosystème qui a pas mal de fonctionnement et de résonance. Un gymnase qui intervient sur des missions de R&D très techno, et c'est excellent. La partie Ingimax, dès lors qu'on a une activité avec une prétention économique, c'est comment on va jusqu'à un marché, et donc on est capable d'accompagner là-dessus. Totem, une agence digitale qui fait des belles réalisations sur du React. Et puis un lab qui s'est monté ici pour travailler en R&D interne sur des sujets tech, il y a des visions, et puis qui avance avec le jeu de réalisation ici. On a une petite galerie, ah oui, et puis on a évidemment autour de ça la capacité de travailler depuis un lab avec très vite un accompagnement sur l'industrialisation dès lors qu'il faut les mettre en prod. Et ça se passe parce que tout ça fonctionne ensemble. On a une capacité d'intervention à la fois sur la R&D avancée, comme vous le feriez dans la R&D d'un grand groupe ou d'une grosse tech aujourd'hui, et puis la possibilité d'avancer très vite sur des POC, et puis la démonstration rapide que ça mérite d'être fait. Et tout ça n'a de sens que parce qu'on travaille l'usage et la préoccupation UX qui est centrale dès lors qu'on se pose une question de pourquoi on le fait. Autour de ça, on a travaillé sur des sujets qui fonctionnent en vision, en machine learning et puis en réalité augmentée, avec des applications pour différents clients et puis des industrialisations qui suivent et qui sont en train d'arriver chez ces partenaires. Que ce soit dans le domaine du transport, que ce soit dans le domaine de la grande distribution ou de PME industrielles qui sont leaders sur leur domaine, qui sont en train de se préoccuper de la digitalisation de leurs activités, de comment renouveler ce qu'ils sont en train de faire et ce qui a fait leur force jusqu'à présent. On recrute aussi, j'en profite, si ça vous dit de venir voir ce qu'on fait, participer avec nous à cette aventure IA et Vision.
Qui est de Inzima ici? Il y a toi et qui d'autre?
Il y a quelques-uns du lab, là, et
voilà.
puis quelques experts qui sont en mission ailleurs, qui ont fait le déplacement jusqu'ici.
D'accord, super.
Donc Marc, Mayedine, notamment, et puis Céline qui s'occupe de l'organisation. Autour de ça, on est ravis que vous soyez là, et on espère surtout que vous passerez une bonne tranche de rigolade autour de ces sujets et de ce qui se passe après, et des discussions. Merci, et puis à bientôt.
So I guess the next speaker would be Erin.
Okay. Est-ce qu'on peut relever en fait sur comme ça? Il y a un écho aussi. Ouais, mais bon. Don't you try? And I thought we should be good. Bonjour.
I don't know very much French, but bonjour, my name's Erin Liddell. Thank you for having me. I'm here to talk about automatic machine learning tonight and also the H2O machine learning library, which is what I work on in my day job. So I'll also mention that it's special to be here because this is a joint meetup with the WiMLDS Paris group, because I started the WiMLDS organization in 2013 in San Francisco, and now it's like 30 different chapters, and this is very big honor to be here and be at a meetup. It's very fun to see it become such a big thing, and they're huge on Twitter. You should follow them. They post a lot of good pictures and stuff. So also an honor to be at, I think I was told that the Paris ML meetup is the biggest meetup in the world. So there's
In Europe.
in Europe. Okay,
No,
so
it's one of the ones.
also a big honor to be here. Okay, so let's see. Well, first, let me just tell you who I am. So I work, I'm the Chief Machine Learning Scientist at H2O AI, which is a company which I'll tell you about here on the next slide. It's a company in Silicon Valley, and it was founded in 2012. And so H2O is the name of the company. It's also the name of the software that we produce, which is a machine learning library, or you could call it a platform because it has sort of its own set of distributed computing functionality as well as machine learning. And it's open source software. And if you know a little bit about the different open source licenses, it's Apache 2.0, which means you can pretty much do anything you want with it. You can make H2O version 2.0 and sell it. I'm not suggesting that you do that, but you could. So it's a very liberal open source license that we put to encourage businesses to use it. So it's written in Java, but all the algorithms are written in Java, and the distributed computing platform is in Java. But we know that data scientists don't like Java, so we have an R package and a Python package, and you can use it from Scala, or we have a web interface in which you can write no code and just click to train models. So. Okay, I'll tell you more about H2O in a little bit. So this is what I'm going to talk about. So I'll describe the H2O platform first, and then I will talk about what is automatic machine learning, or AutoML. And then I'm going to introduce the H2O AutoML functionality. So that resides as just a function inside of the H2O library. And then I'm going to show you, give you some tips and how to be successful using it. It's very simple. That's the whole point, is to take away all the parameters that you typically have with a machine learning algorithm and just give it your data set, tell it to run for a certain amount of time, and then whatever metric you're trying to optimize, and then it just goes and does its thing. And then if we have time, I'll do a short demo. I'm just curious, are there more R or Python people here, or neither? So if you're R, could you raise your hand? Okay, so not too many R people. Okay, Python? Oh, wow. Okay. Well, I guess I'll do the demo in Python. Okay, and so if you want these slides, I don't know if you can read that URL. It's kind of hard to read on the screen, but it says tinyurl.com/Paris-AutoML. And I could also post these onto the meetup page later. But that's just if you want to download the slides where you can get that.
It's already available to the people who could not make it and actually are looking at it through streaming.
Okay, great. Okay, so you should be able to find these if you would like to. Okay, so first I'm going to talk about what H2O is as a platform. So I already told you a little bit about it, but just to give you more information, so it's a distributed machine learning platform, which means that all the algorithms can run in multi-core or on multiple nodes. So if you have a cluster, you can run it across multiple nodes. A lot of people just use it on their laptop and take advantage of the 8 cores that they have on their laptop. So whatever is comfortable to you. And then I mentioned all the algorithms are written in Java, but we have different APIs available, so you can use it however you want. So it's an R or Python library called H2O, so you can install H2O or install from CRAN on R. And then one of the things, so we created this library, so it wasn't an open source project and then became a company. It was a company from the very beginning. So we have like different goals perhaps with the library. And one of the goals was to make a library where it's easy to deploy to production. So that's why one of the reasons that they chose Java when I wasn't around when they first made these decisions. So so some other people decided to use Java. And then you can export the models. If you're sort of just doing data science, you can export them as binary files on your computer, or you can export them as pure Java code, and then you can compile them into your application. And then you get very fast prediction performance. So that's typically how people productionize it. And then at the time when the company started, that was 2012, if you remember, way back when. That was the Hadoop era. I don't know if that's still happening, but Hadoop used to be very, very popular and everyone was using Hadoop. So this was supposed to be a machine learning library that scaled on Hadoop. And then Spark came along, and then we made it scale for Spark. And then, but you don't have to use any of those technologies. So if you don't use any of those, then you can just use it on your computer. So, but if you do, it integrates tightly with each of those. Okay, so, and then here's my most technical slide of the presentation. So I'm just going to introduce like 2 concepts that we have in H2O that relate to the distributed computing. So there's something that we call the H2O cluster, and the most common mistake that people make when they first hear about this is they think it's an actual cluster somewhere and that there's some sort of H2O cloud where we're computing everything for you somehow. So that's not the case. So when you're running a cluster, you're running it either on your laptop or on Amazon EC2 or on the machine at your work. That's what we mean by the cluster. And it's just the name for the Java process where everything happens. So, and the reason we call it a cluster is because a lot of times people are using this across multiple machines, so it's kind of like a cluster. So that's where all your data lives and all your models, and everything happens in the H2O cluster. And really, it's just a shared Java process. And then we have something called an H2O frame, which is essentially the same thing as like a pandas data frame or an R data frame, and but it's just our own thing that we have, and it's distributed. So if you do run it on a cluster, there'll be some rows on one machine, some rows on another machine, and everything happens in a distributed setting. And the point of that is that you should be able to train models on data sets that are bigger than the RAM of a single node. So that's how we divide up the things. But when you're working with H2O frames, we made it so that you don't have to learn a new way of slicing frames and subsetting. It's just all what you would expect from pandas, essentially, or in R Python. Any questions so far? Okay. So that's just some technical background. So then the library itself, in terms of machine learning, the things that we offer are a bunch of supervised and unsupervised machine learning algorithms that we have written from scratch that are all distributed. So it's not as big of a selection as you would say get in say scikit-learn. So part of it is that not all of those algorithms scale in a distributed setting in the way that we do. So we don't, for example, SVMs don't really scale in a distributed way that's reasonable. So we just don't have SVMs. And then we try to offer what's good and popular, like gradient boosting machines, random forests. We do have one type of deep neural network, GLMs, etc. So, and other things that we do automatically that you wouldn't, in some other libraries you have functions to do all of these things like imputation of missing values, normalization, or one-hot encoding, all of these things that we do automatically so that you don't have to write code every time to do them. And then something called early stopping. So in iterative algorithms like gradient boosting machine or deep neural networks, you have this training process that goes on, and at some point you have to decide when to stop. And if you go too far or you train too long, then you can overfit your models. So you have to sort of manually decide when to stop. And so we have some functionality in there that will stop early for you. It kind of checks using a validation frame if you're starting to increase validation error, and then it cuts itself off. So that's kind of a handy thing that I like to use. And then of course we have all the things related to machine learning like cross-validation and grid search and random search. And once you have the models, we calculate variable importance for all the models and a bunch of evaluation metrics that you might use in machine learning. And we have different plots as well. So that's kind of what we're offering. So, okay, so now that you are just a little bit familiar with what H2O is, I'm going to talk about automatic machine learning. So how many of you have heard about automatic machine learning or some idea? Because it's a little bit self-explanatory, but also pretty vague about what does that mean. And it's not a well-defined thing, I don't think. So it sort of relates to any sort of automation of the data science process, I think. So that could include data preparation, so actually getting your data into a tabular format that could be read by machine learning algorithms, or things like doing feature selection or feature extraction, or just any kind of feature generation from the existing data set. And then sort of once your data is ready to go, then you would want to probably generate a lot of models automatically in some way. So There's a lot of different ways to do that, but the key here is you probably want to do a lot of that. Typically, there's not a lot of AutoML tools that work by training 1 or 2 models and just sort of magically predicting what the best hyperparameter value should be. You end up just training a lot of models. So that's just part of the process. And then this is sort of an optional piece at the end. So once you have all these models, if your goal is to get the best model, then one thing you can do is ensemble them together. So that's sort of optional. That's something I like to do, and I include that in the H2O AutoML, so I add that as another component. A lot of the other AutoML tools also do some type of ensembling. And I'll just mention, so there's a couple other open source AutoML tools. So there's one called AutoScikit-learn. There's one called Teapot. There's something called AutoWeka, which is a Java tool. And there's not a lot, but there's a handful. And so I'm kind of working with a lot of those authors right now. We're trying to do a benchmark of all the AutoML libraries that are open source right now, because there isn't really a good one. There was a terrible one that came out on archive. There's not a good one. So that's important. That's actually why I'm here. I'm here at INRIA in Paris for the week, working on some of that stuff. So and then there's proprietary tools as well. So there's H2O also has a proprietary AutoML tool called Driverless AI, which is similar in the goal of the H2O AutoML open source, but it has a lot of automated feature engineering. And so that's kind of like the thing that you pay for, essentially. So, and I work on the open source tool, but that is my closest competitor is within the same company, I guess. Okay, so, all right, so I'm just going to talk a little bit more about what do all these terms mean. So I mentioned a little bit about data pre-processing. So these are just things that you could do as a data scientist. So then, of course, you could try to automate some of these things. And some of the things, well, I mentioned the first 2 bullets already, but the last bullet is also very important if you have high cardinality categorical variables. So if you have columns in your data that have a lot of different values, the example that I usually use is zip codes, and I don't know what postal codes or something that you call them here, basically postal codes.
Postal codes.
So there's, in the US, there's like 50-something thousand zip codes, and a lot of data sets, not a lot of data sets, some data sets would have a column that's zip code, and you treat that as a categorical, and so there's 50,000 levels, and then most machine learning algorithms would just sort of explode when they saw something like that. So you have to do different types of encodings of these what are called high cardinality categorical columns. So that's important. So you don't want your machine learning algorithm to blow up. So being able to sort of handle these cases is important. So that's all within sort of the data pre-processing area. So right now I'm speaking generally. I'm not speaking specifically about what's in H2O, and then I'll show you the same slide with what we have in H2O right now. And then for model generation, a couple of different ways that people do this. The one that you're probably most familiar with is what we call grid search, or sometimes it's called Cartesian grid search, to differentiate between random grid search or random search. So this is just basically, in the random case, generating a bunch of models randomly by sampling parameter values. So if you have, let's say, a random forest, you might look at the maximum depth of the trees or the sampling rate, and just kind of, as a data scientist, you have to know what good ranges for those parameters are. So that's kind of the hard part. And that's the part that prevents new data scientists from getting really good models unless they train so many that they just happen to stumble upon a good one. It's kind of knowing which hyperparameters to tune, and then what sort of ranges that you want to look over. So that's one way to generate a lot of models. Then there's another technique called Bayesian hyperparameter optimization. And that is kind of a very different approach, where it's an iterative process where each time you train a model, you sort of learn something about how that set of parameters performed, and then you pass on that information to this secondary model that's keeping track of that, and then you train it, and then that model will suggest a new set of parameters, and you try that, you report the score back to the other model, and it learns. That's why it's called Bayesian, because you're sort of learning from historical data or prior data. And so the goal there is you're sort of doing a smarter search, so you get to the best model or to a good model more quickly. But one drawback of this approach is that you can't do it in parallel. You have to do it in a sequence, so it takes longer. But there's a lot of studies that compare random grid search and Bayesian hyperparameter optimization. So if you're interested in how they compare, you could read these studies. But essentially, with random grid search, if you run it for, let's say, 2 times as long, you'll still get to the right model, but you don't have to parallelize and things like that. I'm sort of paraphrasing the studies, but yeah, so there are 2 different approaches. And another thing about this technique is the models often just get more similar to each other as you go on, because it's kind of narrowing in on what it thinks is a good area. Sometimes it'll select something way out there to kind of sample a new space, but in general, the models are more similar than the set that you would get with a random sample. And then, okay, and so then for ensembles, 2 types of ensembles I'll mention is, one is called stacking. How many of you have heard of stacking or stacked ensembles before? Cool. Okay, so that's my favorite kind of ensemble, but and that's what we have in H2O right now. So what that is all about is training. So basically, you use machine learning to learn what the best combination of the models is. So there's a secondary learning process, sometimes called meta learning, where you train a model on the outputs from the base models, and then using the same original response column, and it learns how to best combine that data and predict the outcome. And you'll see a lot of this on Kaggle.com, the data competition website. So a lot of stacking there. Sometimes it's called super learning, depending on who you talk to. So same thing. And then there's another type of ensembling called ensemble selection. So how that works is you basically, it's a greedy approach where you keep adding, I think you could probably do it the opposite way where you delete models, but from some big collection. But basically, the most common way of doing it is you just keep adding models from your collection, or maybe you don't train them in advance and keep training them and then add them. And then you basically stop whenever adding new models starts to hurt the performance. So it's just sort of a different approach. And in my experience, stacking works better with diverse sets of models. And this is also not a general rule, but just something to notice. So stacking works well with sort of a diverse set of models, and ensemble selection works better if you have sort of a similar selection of models. That's maybe not always true, but that's something that I noticed. Okay, so that's just kind of, these are all things basically of machine learning, but then of course automating them requires you to address all these items. Okay, so right now I'll show you what we have in the H2O AutoML function. So we have, like in all H2O algorithms, we do this for free. So you automatically get imputation, one-hot encoding when it's necessary, and standardization when it's necessary. And what we're working on right now is target encoding. So this is a useful technique if you have those high cardinality columns. So we're adding that to H2O right now, and then that will go into AutoML. We're not, I mean, probably at some point we'll address feature selection, feature extraction, but I think maybe those are less valuable than some of the other things that we could work on, immediately at least. So, and then for model generation, so these all kind of go together. So with the first version of H2O AutoML, it's been around for about a year. My goal was to just use everything that we already had inside of H2O. So we have random search, we have stacking, So, well, that's a good start because random grid search and stacking work really well together. And then we also tune the models individually. When I was mentioning early stopping, that's what I mean by tuning the models with the validation set. So these are the things that we have here. And so I'll kind of summarize that more clearly. Well, first I'll mention why these are good, and then I'll summarize what we have. So these work well together, and the reason that that's the case is because stacked ensembles perform well if the models, what we call the base models, are individually strong. So this is different from, let's say, ensembling a bunch of decision trees together. That's one type of ensemble, we call that like a random forest or a GBM. But generally we want to put like good models to start out. So things that are fairly strong, like GBMs or gradient boosting machines or random forests or deep neural nets or SVMs or whatever types of things. So, you know, just they don't have to be great, but they just have to be kind of good. And then stacking works well when the models in the set make uncorrelated errors. So what that means is when they fail differently. So if there's some, you know, instances where the random forest does a good job, but the, let's say, SVM doesn't, then that's a good situation because as long as somebody is doing okay in the ensemble, then you're in a good position. So so that's actually why that stacking works well with random grid search, because if you think about what you're doing with random grid search is that you're getting a very diverse set of models because you just sort of randomly created them, so they're not similar in any way. And then and if you do that to all the different algorithms that you have available, if you do random grid search for GBMs and then for deep neural nets, you get an even more diverse selection. So so that's why these two things work well together. It's you know, there's a lot of different approaches to AutoML. This is just one of them. One thing that's makes it a little bit easier in H2O to do AutoML is that the tool is very fast. So it's a lot faster than other libraries. So you can accomplish more in the same amount of time. So you kind of have an advantage, more models to choose from in a fixed amount of time. So yeah, so, and actually the reason that I found out about H2O, I think it was in 2013, was that I was doing a benchmark of random forest libraries. 2013, that was the most popular algorithm that I knew about before GBMs came along. So that was the year of the random forest. And so I was interested in comparing all these different tools, and I took, you know, looked at scikit-learn random forest, R random forest. I found this H2O random forest that claimed to be so fast, and then another one that was a startup that I worked at, which no longer exists, but they also had a random forest. And then H2O is way faster than both R and scikit-learn, and so I was like, oh, this is an interesting library. I'm going to look more into this. And actually, since then, the scikit-learn people rewrote all their decision tree code, so it's actually much better. And so that was actually, I think, a result of looking around and doing this benchmarking. So that was a good benefit of that blog post that I wrote. Okay. So here's just an overview. So we did, you know, basically the AutoML algorithm itself is inclusive of all the data pre-processing, and then what we do is we train random grids of different algorithms. So the part that we've sort of added value to this is by choosing what that random grid should be, because that's kind of something that takes some experience as a data scientist, at least to, you know, narrow the focus a little bit, so you don't have to train so many bad models to get to the good ones. So you know, this is just a sort of first attempt to define what we think is a good grid. That this will probably evolve and change over time as we do more benchmarking. But right now, you know, we've selected all the different hyperparameters that we think are useful and the ranges that we like, and then we do a random grid search over these different algorithms. And then we individually tune them using a validation set. And then at the very end, when we have all these models, we train two stacked ensembles. One of them we train on a whole set, so all the models that we've trained. And typically that's the model that does the best of everything. But let's say you run this for a very long time and you have like 1,000 models, and then you want to put that model into production, and then you think, well, that's a lot of models, because when you have a stacked ensemble, in order to make a prediction with a stacked ensemble, you have to get predictions first from all of the individual models. So that, maybe isn't the best approach if you're trying to productionize a stacked ensemble. So then we have another version where we just take the best algorithm from each of the different types. So we take the best GBM, the best random forest, best deep learning, et cetera. And then we make a lightweight stacked ensemble. And that one usually comes in around, number 2 on what we call the leaderboard. And then generally all the models come after that. So we offer, like, if you want the very best, here's the very best. If you want something that's a little bit more practical that you can put into production, here's another version. And then everything else that you've trained is also available. So then what you get back from running the AutoML is what we call a leaderboard. So that's kind of comes from the data science competition community. They use, on Kaggle, they would have a leaderboard where everybody's ranked and how they're doing. So it's essentially just a data frame that has all your models listed in it, has all the performance, and you sort by whatever metric you're interested in. And then you can see how you've done, and then you could choose the leader model if you care the most about performance, or you could choose some other model if you have other other things that you're thinking about. Maybe interpretability is important, so you want only GLMs or something like that. And I'll just show you just the interface to H2O. So this is the web interface. So this is probably, I mean, a lot of people use this, but probably in this community, maybe not the most important interface. A lot of Python people in here, but I don't know if you can see it. But basically, whenever you start up an H2O cluster, it also starts a web server, and then it runs this interface that we call H2O flow. So at any time, if you're using the Python package or the R package, if you can always type in a IP and port in your browser, and it will bring up this GUI. So if you trained models from Python or R and you wanted to look at plots that it creates automatically, or just poke around, you can use this. Or there's just different. You can go back and forth between this flow GUI. But for AutoML, basically, it just gives you all the arguments that are available. So really, I'll just kind of skip over this and show you the next interface, because essentially you point it to your training frame, tell it the column that you're trying to predict, and then you can do certain things, but there's pretty good defaults that I'll explain in a minute. So at first, I just want to show you just the set of minimum arguments that you would need to run AutoML. So this is our, maybe I'll show that for a second, and then I'll skip over to Python, because I know you don't care. Okay, so here's the Python version. So we import H2O and get the AutoML method. And then the first thing that we always do when we use H2O is start up the H2O cluster. So that's what the H2O.init is. And you can start it, there's a lot of different arguments for starting it on a certain IP address, or with a certain amount of memory, or a certain number of cores, or something like that. But generally, if you're just playing around, you don't need to set any arguments, and just run H2O.init. And then you import the training data. So you can import from all different types of formats or databases or whatnot. But here's the most simple example, just a CSV file. So this is essentially like pandas read CSV, except for it's parallelized, and it goes directly into the H2O cluster, which is just the Java memory. It never goes into Python memory. So that's something to be aware of. And that's for efficiency reasons. So when you're using H2O in Python or R, it's really just an interface to what's happening in Java. So anytime you type, you see this train object here, that's not living in Python. That's just a pointer to where that data is in the H2O cluster. But you can treat it like it's right there in Python. You can subset, you can do different data munging tasks, etc. So to set up AutoML, really the only thing you need to do is tell it how long do you want it to run for, or how many models do you want it to train. So in this case, we're saying train for 600 seconds, which is 10 minutes. And so first we create an object of type H2O AutoML and specify anything to do with that. So the most important thing is how long you want it to run for. And then you train and specify the different data arguments. So if you're used to scikit-learn, what you would see would be an X and a Y. That would be a NumPy array or a data frame. But here in H2O, the slightly different interface. So you have what's called training frame, which is all your data. It includes the Y and the X together. And then we have a little X and a little Y as arguments, and that's just the column names. So Y would be your column, the name of your response column in the training frame. And then if you don't specify X, it will just assume everything that's not Y is your predictors, but you can also specify some subset of the columns by saying X equals, list the column names or the column indices. And we found that that's just a little bit easier just to keep the data just as one piece instead of trying to break it up into different things. And so that was just an API decision. So once you do that, that'll go off and train all these different models for a certain amount of time. So we kind of pre-allocate time to the different things that we think are important. So it actually spends a lot of the time in GBM random grid search, and then spends a little bit less time in things like deep learning or other, random forest and things like that. That will all evolve over time too, with feedback from our benchmarks. So, it's sort of a black box, and it will change over time. And we will only change it if it improves on some large benchmark. So that's kind of the development process in AutoML. Is first just think of what would you do as a data scientist, and put that in a big wrapper, and then just call it AutoML. So that's how this is created. So it just came from I was just getting sick of writing the same code all the time. And then from there, it's very hard to know if you're making changes, if it's improving the algorithm or you're just making it worse. So benchmarking is actually a really huge part of AutoML development. So you have to know for sure if you tweak that grid of the deep neural net, is that actually helping, or are you just overfitting to some couple data sets that you're playing around with? So that's why I'm here working on a lot of benchmarking, so that we can build a system that the whole community can use, that so we all know where we're at and we can actually make progress instead of just moving things around and overfitting to our data. And then what you get back is one of the things is a leaderboard, and the leaderboard looks something like this. So there's some columns missing just to make this short and fit on the screen, but basically, so this would be an example leaderboard for binary classification. So this is a real leaderboard that was trained on this data set called Higgs, which is a data set you can find on the UCI-ML website. It's a binary classification problem. I think there's 18 numeric columns, and it has something to do with the Higgs boson experiments. I should know because I use it for all my demos, but it's something like that. And so I think this is a 10,000 row subset, and I just ran this for, I'm not sure, maybe a minute or something. And so it trains this many models, and what we see at the top is the best model here ranked by AUC. So that's the default metric for binary classification, but you can change that to whatever you like. And so it's sorting by this column here, and we have an all model stacked ensemble. Then the next one, which we call the best of family, that's the one from each type of algorithm, and then a bunch of different GBMs, and then that stands for distributed random forest below, and then XRT stands for extremely randomized trees, which is just, it's actually just another type of random forest that's more random than a random forest. But those are, different than a regular random forest. So we want to have more variety, so we put that in there. And then some other GBM that did a bad job, and then sad GLM at the bottom, not doing so well. So that would be just an example. And then what you see here, these are model IDs. So you can just, everything's stored in the H2O cluster and everything has an ID. So all data sets have an ID, models have an ID. And so you can just grab them at any time and then look at the parameters that it used or anything about the model afterwards. Okay, let me just check. I'm doing on my time.
We're good.
Good?
Yeah.
Okay, so so here's some pro tips. So it's pretty easy to use this, but I'm going to give you a few tips. So this is like...
But the leaderboard is on a training set.
Good question. So it depends. So by default, it will be 5-fold cross-validation. So these will be cross-validated metrics. And if you want, you can specify a specific training frame that's just to score the leaderboard, if you have a use for that. So by default, we would just use 5-fold cross-validation. You can change the number of folds if that's too many, if your data is very big. Or you can just provide it some like little test set. Okay, so just before you start training a whole bunch of stuff and running a huge AWS bill, here's just some pro tips. So this is what I just mentioned, this leaderboard frame. So there's 3 arguments. There's training frame, validation frame, and leaderboard frame. And the only one you need to specify is the training frame. And if you, this is my second point here, maybe I'll talk about this one first. So if you only provide a training frame, it's going to chop off a little piece of your data to use for the validation frame. And that's for early stopping for all the algorithms. Right now it's 20%, and I feel like maybe that's too much. So probably after benchmarking, that will reduce to something maybe more like 10%, I don't know. Or a function of the size of your data or something like that. So if you don't specify a validation frame, it will chop off a piece for you. Or if you want to specify your own, 5% or 30%, whatever you want, then you just pass along the validation frame argument. And this is also optional. Leaderboard frame is if you want to score the leaderboard on a specific data frame, like a test set, then you can pass that along and then the leaderboard will be scored on that. But generally, it's a better use of your data probably to use cross-validation because then you're not sort of wasting data just to score the leaderboard frame. Okay, so then we also try to make everything very automatic, but then also we know that a lot of people are sort of experts at machine learning and they want to be able to tweak all the knobs themselves. So, one request that we had when we first created this was the ability to turn on and off different algorithms, because typically for a particular data set, they don't all work the same. So maybe there's some where trees work better and you want to get rid of the other ones, or vice versa. So yeah, so one example is if you have very sparse data, let's say from text, then maybe you don't want to deal with trees, or maybe you do some dimensionality reduction or something like that, and then deal with trees. But yeah, you can exclude whatever algorithms you want. You can only exclude them by class. So you could say no random forest. You don't get to say right now I don't want this random forest and this random forest. But we will add that in the future so that you can modify and augment the AutoML process. So we hope to add another API endpoint where you can say, I want you to also look at these specific models in addition to what you have, or I don't want you to look at these. And we want to make it more of a tool for doing machine learning and with very good defaults, but the ability to tweak it. So, and then another thing that sometimes I still forget is that we set the max runtime seconds to 1 hour by default. And so that's just kind of so that it doesn't run for infinity. So, we chose, I think we might change this, I'm not sure, but because basically what will happen is we have this max models as well. So if you specify max models as 100 and you don't set anything for max runtime seconds, it will still stop after an hour. And sometimes I forget that. And so it stops after an hour and then I don't have all my 100 models and I'm sad about that. But you can restart the AutoML process. So it's not that terrible. So your time is not wasted, but just something to be aware of about reproducibility as well. So the time-based stopping is probably not reproducible. So if you run it once and you have a certain number of processes running on your machine at that time, and you run it a second time, it might have a different amount of resources. So even though they both trained for 1 hour, maybe one was able to train more models than the other. So that's not a very reproducible way of running this. So if you want to ensure that it's almost reproducible, I say almost because our deep learning algorithm is not reproducible when you run it on more than one core. So it's reproducible up to a point in which deep learning is not, and then if that's in your stacked ensemble, then that will also not be reproducible. But if you want everything else to be reproducible, you can use max models, and then if you want it to absolutely finish the 100 models that you told it to, then you should increase the max runtime seconds to some large number. And I think we might just change that so that we force you to specify one or the other or both, and then, yeah, I think it's a little bit confusing. And then just a reminder that all the models are stored in the cluster memory. So that means that if you're going to train it for a long time, you have to have enough memory to store all those models. So I remember I told you about H2 init. One of the arguments that you can specify is how much memory you want to allocate to your cluster. So by default, in Python, it works a little bit differently in R and Python, which is a bug, but in Python, it will take like 20% of your RAM by default, which is, if you're running it on a laptop, maybe not that much. So you might want to set that to be something a little bit less than the amount of RAM on your machine. So here's an example where you say I want 80 gigs of RAM.
And what about R?
In R, it defaults to 4 gigs always.
Okay.
And that's to do with just how you specify arguments in R. Like in Python, all of our defaults are none, and then it asks Java what the default is. And then in R, it specifies something. So it's just a string that says 4G. So anyway, it's kind of a weird thing, but most of you are Python. So okay, so then after you're done, this is like your future job situation. Pressing buttons and sleeping, if you have a job. Anyway, yeah, maybe I'll skip over this. This is just so I kind of skipped over this other way of stopping. So if you can also stop based on performance. So if you set it for like 1,000 models, but it's silly if it's training new models that are not overall improving the performance of the collection. So you can do things where you control how the AutoML process itself stops. So there's like an early stopping process for that. So you can specify things that's basically say like if it doesn't increase by this amount, like if the best set of models, if you rank them all by performance, if it doesn't increase by a certain amount over a certain number of iterations, then stop training. That's just to kind of like not waste your time and resources. But generally, you probably don't have to mess with that. But anyway, if you're finding that it's kind of stopping too early, then it might be because this is kicking in, so you could adjust these parameters. And then I mentioned that one thing that you can do that's kind of useful is if you want to just train, let's say, for 20 models or 50 models, you can start there and then you can start it up again. So there's something called project name. So that's just an ID basically for the AutoML process. So you can execute the train method once and then for 50 models and then look at the results. And then if you execute it again, as long as the project name is the same, it will just keep adding models to your leaderboard. And the only thing that you have to be aware of is if you have the same seed, it will produce essentially the same models. So if you do it a second time, you want to change the seed. But that's kind of just a practical thing. So you maybe don't want to wait for, 8 hours to see what your results are. You can just do it in iterations. And then all these models, you can just save them like you save any H2O model, including the stacked ensembles. So that means you can save them as a binary format if you're just needing to save them and you're not ready to go to production yet, or you can export them in a format that we call Mojo, that is for productionizing. Okay, so then I'm just going to sort of point you to where this tutorial is because I don't want to take too much more time. So there's a tutorial here, and this is, we have a conference that we call H2O World that we've been doing like various places, but this is the last one we had in California. But we actually are having H2O World, maybe Joe will talk about that, coming up in London on October 29th and 30th. And I think that maybe we have some sort of discount or something that we can give all of you if you want to take the train to London. So if you click on this tutorial, oh, I guess I don't have internet, but let's see. Think about that. Let's see if I can create a hotspot on my international 2G speed. Oh, let's see if it works.
There's a guest Wi-Fi that works.
Is there?
Yeah, I tried.
Is there a password?
No,
Oh,
just wait.
it says there's a password.
Amazing.
Yeah, there is a password.
I can try my phone and see what happens. I just needed to load one web page. Let's see how long that takes.
Okay.
Well, it will load, but it will take.
Can you use your phone or?
Yeah, I'm using my phone. It's
Okay.
just
You
my
can
international plan. It's very slow speed.
you try to use mine then.
Okay. But I think, it's almost there.
It's getting there.
So what I'm pointing you to is we have a repo. So the organization on GitHub is called H2O AI, and then we have H2O-3 is the main H2O repo because it's our third incarnation of H2O, and we also have a repo that's called H2O tutorials. And so this is just the AutoML tutorial is here, and we have the same code for R and Python for the same tasks. So there's two tasks here that you can sort of learn about AutoML. So there's one for just a binary classification example, and then there's another one for regression. And I might be pushing my luck by trying to open that up, but we'll see. So basically, I was just going to show you a demo, but, well, I wasn't going to run the demo. I thought that would be too daring, but this also is too hard. Okay, so I just want you to know where to go if you want to learn how to use it. So essentially, you follow that link, and it will work you through just basically the code that I showed. There's not too much there, so just import the data. This is a data set where you're predicting product back orders, so it's a binary classification problem, and then you train AutoML for a certain amount of time, and then we look at the results. And then I think at the end there's also there's also a place where we look inside the ensemble. So I'm going to just skip to that because that's the only new thing here. So one thing that's kind of fun to do when you have a stacked ensemble is to look inside the meta learner and to see how it's combining those base learners together. And so you can use any algorithm for your meta learning algorithm, but the most common one that I've seen people use is just a GLM. And you would think maybe, I would say that one's the easiest one to do without a bunch of training and grid searching. Sometimes if you use a GBM or like a Hors, it can also be good. But generally, a GLM does a pretty good job, and it's not gonna mess anything up. So that's the default middle learner that we have in H2O stacked ensemble, but you can try other ones if you want. But one of the nice things, well, if you use any meta learning algorithm in H2O, it will give you some sort of variable importance. For GLMs, it's just the magnitude of the coefficient, so it has a more direct meaning. But what you'll see in any case here is just sort of a ranking of how it's combining these base learners together. So and then maybe it's maybe not exactly the order in which they appear on the leaderboard either. So it's kind of interesting, and you'll see one thing I'll just point out is like at the bottom here. We have two models where the stacked ensemble is completely ignoring their input because they're so bad. So there's a deep learning model there, and there's a GBM that just happens to have a really bad set of parameters. And so you can kind of maybe learn more about your problem by looking at this, but that's just kind of a fun thing to do if you're new to ensembles. And then pretty much done here. I'll just put up the last links. So again, if you download this slide deck, you'll get all these links to all of our tutorials and our we do a lot of meetups, so like all the presentations like this one, and videos, and Stack Overflow is the best place to go to ask questions about H2O. And then we also have a Google group, but this is kind of trying to phase that out a little bit because it's more easy to index questions on Stack Overflow. And of course, if you want to contribute to H2O, there's a link to like a file in our repo that tells how to do that. That's awesome. You don't have to know Java. You could do just Python or R or just documentation or whatever. That would be great. And then that's how you can get a hold of me if you have any more questions. And then I guess I'll just leave it at that. So thank you very much.
Are there any questions for Aaron?
Thank you for this very interesting talk. You mentioned many examples arising in the field of supervised learning, but in the future, do you plan to consider reinforcement learning as well?
That's a good question. I think with H2O, so H2O itself is a CPU-based library. So we have some other different libraries now. So we have something called H2O for GPU, the number 4, H2O for GPU. And that's GPU. So I guess I'm kind of getting to your question in a roundabout way, but probably for reinforcement learning, maybe you'd want to use deep learning for that. And so maybe then you'd want to use GPUs for that. And so maybe you would end up in sort of a different software package. So probably not for this particular package, we wouldn't do that, but we want to have the best AutoML. So if that requires bringing in some other library and bundling it with H2O in some way, we would do that. So that's something that we did with XGBoost. So probably a lot of you have heard of XGBoost. It's a great GBM library, and for a long time we were just kept tweaking our GBM. We wanted to beat XGBoost so bad, and like sometimes we did and sometimes we didn't. But then we just realized that we could just put XGBoost inside of H2O and then stop playing that game. So that's what we did. So that was the first time we took another third-party open source library and bundled it inside of H2O. So there's now an H2O.XGBoost. Well, I forget what it's called in Python. It's what I call H2O XGBoost estimator. And so we added that maybe about 6 months ago, and it took a lot of effort to get the memory management right. But now that's really solid, and that's going into AutoML soon. So now on the leaderboard, you'll see XGBoost. It's something that we're working on right now. So the point is, if there is another library that we can make use of, we're not opposed to bringing it into H2O and creating a sort of interface on top of it.
Another question?
You said that you're using a bunch of models to train and compare. Can we load our own models to be included in a leaderboard?
So in the future, we will be able to. But right now, what I would say is you could just take the leaderboard and you just grab the column of model IDs. You can remove the two stacked ensembles, and then you can add yours to that, your model IDs that you created, as long as they're H2O models, which I guess I'm assuming, but maybe that's not what you're asking. And then you can just do a stacked ensemble yourself. So maybe that would be a nice thing to add to the AutoML tutorial, to show you how to bundle that in. But we have plans to expose like another argument where you would maybe pass in like a JSON string that says this model with these parameters train that one too. So that's just more of a API thing that we need to add. Yeah.
Hi, thanks Aaron for the presentation. I've never used AutoML before, but after this, I think I may be give it a try later. But it's gonna kill a lot of fun doing data science. But the thing is, the question I have is, you say you use two-level stacking to the AutoML, and I'm asking that in the second level, so we have the choice to use either linear blending or some other more sophisticated model, right? But by default, it's a linear blending.
Yeah, by default it is.
And so I'm wondering the coefficient on the second level, are they optimized using a holdout set? We don't that are not used in the first layer, or how manage this kind of?
Yeah, they are. So our GLM, which is what we do by default, you can pass a validation frame and optimize to that. So and we have early stopping on our GLM and stuff like that. So it will be optimized to a validation frame.
It means this data is kind of held out during all the first layer optimization phase.
So the same validation set could be used to tune all the base models as well, and then we use the same validation set.
Okay.
So
okay.
Yeah.
And is that possible? On the second layer, we only have the choice to use either linear or some other model. Can we add another layer after that, like a third layer?
So not right now in this AutoML library, but one of my colleagues, Marios, he has a library called StackNet, and it's however many layers you want, basically. Yeah. So he works at H2O. He's famous Kaggle grandmaster. So what we did was hire a bunch of Kaggle grandmasters to help, primarily with the driverless AI tool to do all the feature engineering stuff. But he still has the StackNet library. So if that's something that you want to try out, that's what I would recommend.
In case when we stack too many layers, we have some kind of information leak after each layer, because each time when we validate something, some information will be used to validate the first layer before. So that's kind of
So I think his library handles that properly, and if it didn't, he probably wouldn't be so good at Kaggle.
I see. So so this H2O product we have 2 layers, right?
So for this right now we have 2 layers, and probably that's something that we look into in the future, but probably not before doing some more obvious things that are easier to do first.
Okay, thank you.
Another question for Ari. Yes.
When you don't use AutoML, the difficulty is to choose the good models and to choose the good hyperparameters. But with AutoML, it appears to me that the difficulty is moving from that to choose the good the good hyperparameters that you just described. And so my question is this possible to build something like AutoML of AutoML? Because we have to have expertise in the right choice of the hyperparameters that you selected, like time constraints, budget of time, member of the family, or all the models, and all the hyperparameters that you have to select. Yes.
So I think the question is, can you do AutoML on top of AutoML?
Yes, because there are also a lot of hyperparameters, but they are not the same that when you don't use AutoML?
Mm-hmm. So, well, one way you could do that right now with this tool would be to train different AutoML runs with different seeds, and then you could stack those models together, be stacking stacked ensembles together or something like that. That's not necessarily AutoML, but it's a sort of form of that, I suppose. I don't know if that answers your question, but yeah, I think, yeah, I don't know if is that a sufficient answer? I don't know, yeah, thanks.
Another question for Erin. Yeah.
What's in the proprietary version?
What's in the what?
Proprietary.
Oh, okay. So, well, the main difference in terms of modeling is the automatic feature engineering that's in Drivo. So the question is, what's the difference between the proprietary tool? And that's the part that still, in general, takes a lot of like data science expertise. So the idea there would be like you could either pay data scientists a salary to figure out how to do all that, or you could buy that in the tool essentially. And because the modeling stuff is more straightforward actually than the feature engineering stuff. So so that's one difference. And then the way that they also do ensembles and that type of stuff. But yeah, so that's the main difference. And then there's a couple other like little modules that come with it. So there's like an automatic visualization module where it like automatically makes visualizations and tries to figure out which ones are the like most interesting, and it shows you them automatically. And then there's a model interpretability suite. So if you've heard of things like Shapley or Lime, some of these interpretability methods, we have a whole other piece of that that's included. So if you work in regulated industries, you might need something like that. So just the pipelining is a little bit easier to use than in H2O as well.
Okay.
And it works on GPUs.
One last question for Erin. Sorry, you choose.
So my question is, actually I trust the element in a Kaggle competition, and what I found out is actually it's very easy to overfit the train sets. So is there some advice to avoid the overfitting?
I guess so. The question is, she tried out this AutoML. Right?
Yes, this
particular AutoML.
Yes.
And she said it overfit her Kaggle data set.
Yeah.
So I guess one question would be like, how big was the data set? Was it?
Actually, it's very small one, the home predict.
Okay, so so this is kind of an issue with small data sets. So stacking tends to not do so well if there's very small data. So probably like in the future we add methods that are sort of different for the size of the data. So right now we don't look at the size of the data and try to do something smart based on that. We just do the same thing for everything. So I guess I would say one, you could try running it for longer. I don't know how long you ran it for. Or I guess if it's pretty small, it's just.
Actually, what I try is the default parameter, and I just some variation of each user the random forest. So I think it's the small greedy algorithm, so we'll just learn some kind of the buyer in the train sets.
Yeah, so because H2O AutoML is heavily GBM based, one thing that you can do is try to change the early stopping parameters. So there's 3 parameters for AutoML that control early stopping, and they control early stopping of the whole AutoML process, but it also controls early stopping of the grids and then early stopping of the individual GBMs itself. So if they're overfitting, then you probably need to change what's called stopping tolerance. And then also make sure that you're using, we have 2 arguments for metrics. So one is called sort metric, which that's the one that you sort the leaderboard by. And then generally it's the same, you would want to choose the same thing as the stopping metric, which is the metric you control the stopping with. Generally, you want to do that, use the same thing, but sometimes using, like if you have, you care about AUC in a binary classification model, sometimes it's helpful to use log loss for the early stopping, and you might want to, so that's why I separated those two arguments. So you could make sure that you're using those things correctly. And then there's another thing called stopping rounds, which controls how many rounds you look at when you're doing the early stopping. So that's probably what I would try.
Okay, well, thank you again, Erin. I guess next we have Joe Pye. It's going to be using your computer as well.
Yeah.
Okay.
Hi everyone, thanks for staying. I'll just keep you for another 15 minutes.
Bonsoir.
Bonsoir.
Oui. Back to English, sorry. So, I want to tell you about this use case because it's a perfect use case to demonstrate AutoML that you just heard from Eric. This is actually an accident because I didn't plan to make this work. It was like a toy demo that actually worked in the real world. So I'm Joe Bai, I'm Joe Child. You can remember me as a Joe because it's easier to remember for a British guy because they don't remember my name after 15 years. I'm a data scientist. They gave me different job titles now, a lot of job titles, but they drop me into different teams, different things, but I still see myself as a data scientist at H2O. I'm still the only Joe at H2O, so if you want to reach out to me, it's just Joe at H2O.ai. So some of you might notice that I have an Evo Twitter handle, so I use MATLAB a lot before I learn about H2O, open source, and all that stuff. So this is like having your girlfriend or boyfriend's laying tattoo on your forehead. So don't do that in real life. So that's me the past. So I'm back to open source now, so I'm fine. So this is about how to use different packages together in the our ecosystem. So we have H2O, we have Lime, we have Shiny. So this is about telling a story with different tools together. Just a bit about myself. So before I learned about H2O, I was a civil engineer. So I was a boring traditional engineer before I learned about H2O and all the stuff. So somehow I became a data scientist. I worked at Virgin Media, a telecom in UK, and then also at the same time worked for a data science platform called Domino Data Lab in the US. So they are not Pizza Domino, it's Domino in the US. This is actually my first public speaking opportunity in London. So it was the London event. So I presented something that I did as a hobby to visualize the crime in the UK, and that started my career. Become a big data scientist, and somehow I joined H2O. I still don't know how, but I joined H2O because I was the only guy in UK for H2O for a long time. So they have to ask me to do almost everything. So data scientist, sales engineer. I'm actually now in the marketing team. So you see, when you work for a startup, you have to do different things. Because everyone also changed the role so many times. You did China retail. But one of the things that I always enjoy doing is taking photos at the meetup and other events, because it's like a memories of me doing different things at different places of the world. So today I want to ask this for a favor again. This is for GDPR, so not for my benefit. Do I have your consent?
Yes.
Yes. So I will do a photo like this with you all. This is the camera. I didn't do this last time because this is new.
Is it? No, you did it actually last time.
Okay, so
It was already there.
Yeah, okay. So what happens that when I click this button, we'll took a 360 photo of all of us together. So please do all your crazy thing in the background, you can wave. Okay, let's see. You guys ready?
Yeah?
Let's go. Hey, that's part of my job. I'm serious about it. Okay, look, long story short. So this is the final outcome. Yeah, sorry. Thank you. So this is the end result of this toy demo. We started the toy demo. So the actual figure that of the contract is actually a lot higher than 20 million because we cannot reveal the actual figures or the name of the players or the team of the baseball team because there will be legal consequences for IBM. But actually what happened. So how many of you here know or love baseball? Good. How many Americans are here? 1, 2. This happens every time I talk about Moneyball. So no offense to Americans. So we're outside of Europeans or anywhere outside USA, we don't really know about baseball. So that's a fact. Football?
Soccer? You mean soccer, right?
Soccer? Yeah, soccer. Yeah, of course.
You're in France.
Yeah.
World champions.
Who won the World Cup? So I want to. So I'm not going to go really deep on baseball, but I just want to say this is like a business case that you can combine data science and domain experts and some good data to tell a good story and actually make it happen as a business decision. The Moneyball is a famous book and movie. So again, thanks to Americans. So they have they create this movie that so many people never heard about baseball, and then kind of understand actually there's something happening in the baseball industry. They use different statistics to look for some underrated players and then find them before the big team. Say for example, the New York Yankees, they have a big team like a Paris in Germany here. So you want to get the players before the big teams notice them, so you can get them cheap. But then when I start looking at this problem, because I want to step back and see what's the actual real business problem here for the team and for the player. So I see that the forecast that we have, like on the website, ESPN or other websites, they only have the predictions for the next year. So for example, we have the past many years of record, but for the next year, they only have one data point as the metrics to measure how good they are in the next year. But then if you put yourself into the shoes of the players, when you want to sign a new contract, when you want to join a new team or remain into the same team, you want to have a good contract, like 3 to 5 years, because you want to ensure some security to your future. So you don't want to just say 1 year contract and then let's go. So that is for the players, they want to have a 3 years contract at least. But then this becomes a problem for the team, because when they sign up a player, when they offer a multi-year contract, they want to kind of evaluate or estimate the performance of the player in long mid-term. So that's why we're trying to create a project here to try to predict 3 years performance for each player in a baseball team. So this actually wasn't my idea. So I met a guy called David Kearns, so he's the product manager at IBM. But he loves baseball. He's not American. He's Irish. So I don't know why, but he loves baseball. And he came up with the idea, say, okay, we want to get into the market of the Americans. So we want to have something that's closely related to their life. So we'll say, let's do some baseball analysis and put it into IBM, HQL, that big combo. And then we start with some data, like a public data called Layman. So it's like a public data set that we can download as a package or from GitHub. But we then do something really special or interesting. So then comes our captain. So you may not see him from here. This is the guy. So we talked to Agility. Agility is one of the partners of IBM. And then one of the guys said, we have a guy here, kind of knows baseball, and then he may want to do some baseball with you guys. Okay, yeah, let's go, let's do it. But at the time, I didn't appreciate that kind of understatement. So it was the most silly understatement of the world, saying he kind of knows baseball. He is the Mr. Moneyball, so he is the guy. I think in the movie, so they didn't use the real characters as the base of the story, because the real character, they didn't want to work with Hollywood or the filmmakers. So the filmmaker had to find someone similar. So they interviewed Eric Evans and use his story. So he's actually doing this for many years, 30 years or more in the baseball field. They use his own story to create a fictional character in the movie. So that actually is him. So I was like, oh, so he kind of knows baseball is an understatement. So what comes with Ari is his domain knowledge and his data. So again, I said we start with the open source data we call WiMLDS, which is like a pretty high level aggregated data of the player performance per year. But then we have the private data from Ari, because he collects, I don't know how he does it. So for every game, every play, he got the speed of the ball, the location of the position of the ball, what's the end result, whether it's a home run, whether it's a run, all kind of things that happen with the baseball match. He had it in the last 10 or 15 years. So together, we try to use that rich database to enrich, to enhance the Lemon database, to create a better database for machine learning purposes. And that's how we put everything together. Just a quick overview of the dataset. We can see from the left-hand side, that is the open source Lemon database. So we can see how many games a player played last season, how many wins, how many home runs. So many statistics that they use to measure players' performance over the years. But they are like highly aggregated level data. So we only have one number per year per player. So then we have Ari's data. So it's really rich. So we've got the speed of the ball, the spin rate, so all the things that is better to describe the actual changes in the game for the players over the year. So we try to use this, aggregate that to the same level as Lemon, and put it together for machine learning. Okay. So again, so this is how we do it. So we frame the problem as a regression problem. So we try to look at the number value predictions for the next 3 years, and use them to try to predict what are the good players that we should sign for Ari's team. So for that, because I work for H2O, or actually I like H2O AutoML, it's one of the best tool here, because I didn't have much time to build a model, so I used AutoML to build some high quality models on the flight to Vegas for conference. So that become some models for the base of all these predictions coming from H2O. And again, we have two approach, because one of the reasons why I want to have two approach is that I want to show that with Ari's data, we will have a better model than just the Lemon data set. So we try to have the first approach, which forget about the Ari's data set. We just use the Lemon database with the age of the player, the height, the weight, all the different attributes of players, and the historical performance in the past. Frame it as a machine learning problem and predict some metrics like home runs, batting average, and other things about baseball. So you guys don't know about baseball, so this doesn't really mean anything to you. But this is some of the numbers that we use to measure the players. So the next approach is that we try to create a better model. So this time we use the features coming out from our database. So fastball, curveball, speed of ball, all the things to enrich the original Lemon database and use that to predict the same thing and see whether we can get a better model out of this. And of course we did. And that's why we have this presentation today. So this is now showing one of the metric for one player. So this is one of the star player. He's called Chris Sale. He's the best in the league right now. So we're saying that for one of the statistics here, for the whip, which is like a walk and hits per inning pitch. So the lower, the better. So we're saying that this guy, we compare the models that we built just with a Lemon dataset, which is like totally out of the order, way off. And then we have the model, the orange bit here, which is using both Ari's and the Lemon database. So it kind of makes sense to use that as a trend. And then we're using these 3 points here, the last 3 points here. They're like the 2018, 19, and 20. So the predictions for the next 3 years of a player. So what this graph is saying that we predict that this player will do well in the next 3 years, and so on. So this is only one of the graphs, one of the metrics. So we have many graphs together. So just another graph to quickly show you how this is done in terms of training and monetizations. So it's a simple split. So it's not really strictly a time series problem in this case, because I didn't have enough points in the past, because I have to aggregate our database back to 2010. That didn't give me enough like a coefficient to do a proper time series. That's why I just put it into a simple regression problem. But I do create the last training split into the last 2 years. So I use 16 and 17 for the validation, just 2 points. But the best thing is that I have Ari and his domain knowledge in the past many years. So I can ask him to look at those graphs and kind of try to match his expectation in his mind, and he kind of agree with the predictions here. But then this is not enough to convince Ari that this model will work for him. So what I did is to combine another package called Line. So sorry, we may not be able to see it from here. So this is the Line package that works with H2O model. What happens here is that I can kind of give some reasonable or approximate reasoning to the outcomes. So from different inputs, so different input from the feature here, from the vector here, and then using our experience in the past to see, look at different features, how do they contribute to the final outcome? So this is for the batting average. So PA is the batting average. So how do they contribute to the final numbers of the predictions in 2018 and so on? So he's kind of used this to look through the model, look through the predictions, and I gained his trust by doing this with Line. So this is one of the useful way to gain some trust from the domain expert without trying to bore them with the numbers from machine learning output. And finally, because he had about 10 players in mind to look at before he wanted to find one of them. So I need to create something quick for him to navigate through the result. So I can't just copy and paste onto Excel and give him the spreadsheet. So overnight, I created a Shiny app here, which I will try to do it live demo later on. So we can now use a drop-down list or list to search different players and look at the performance and the explanation from Line and try to find the best player that he had with a price tag that they can afford at the time. So that's how it happened during the conference. So this is actually like a demo for a conference. So it was not supposed to be a real thing. So during the conference, he used the app to look for players, and then at the beginning I thought it's just for a photo. So we went to a booth, take some photo, and that's it. And then the time he took out his notebook and start writing down the names and the numbers, and I knew that moment he got serious about the predictions. And he actually marked down the player, and he suggested that to his team. And after 24 hours of medical check, he got a contract, offered a contract to that player. It was crazy. It was crazy 4 days in Vegas. Okay, so let me show you the live demo quickly. So this is the actual application that I gave it to Ari to use. So you see that the main thing is the player's name and some attribute associated with the player, so the weight, birth year, and so on. So what we ask Ari to do is to think about a player. So maybe say I can ask him to think about maybe Alex, and then let's see this. And he can look through different players, and then from different players you can look at the explanation to look at the approximate reasonings to the contribution of different inputs to the outcome. So if he agrees with that, then he look for another players and so on. So he used this app to quickly navigate through different players until we find the one that he wants to sign, and that becomes the actual Moneyball application for demo. We can play with it later on if you want to try it yourself. Okay. So that is mainly my talk, but I want to give you a few more things here, because this Moneyball talk was about a month ago at the ORI AI conference. But then I already have some commitment during the week in Oslo, so I couldn't go. So this guy, so Ari, David Kearns, and then this is Chris. So they went without me. But I asked Erin, kind enough, to talk about actual Apple now at this talk. So I didn't go. But this guy, they went to the Oakland A's Stadium to watch baseball. So this is original Moneyball Stadium, so Moneyball team. So this is the Oakland A's. So he went there to watch a baseball match without me. And then I knew this would happen. So David Kearns just treated me so yeah, I said I'm missing out big time, and he said, yeah, I know that this will hurt you. So that's true. So that's good. Then, if you really want to hear from Ari and David himself, they are coming to London. So this is actually my job now to tell you about Exo AI World London. So what we have is our events in London with our users and our customers coming back to us, talk about the use case. So this time we have Moneyball from Ari and David. We also have people from Booking.com, from maybe from other banks in the UK, They will come and talk about how they use H2O to transform the business. So we have 2 days. The first day is actually about the hands-on training. So we can learn about H2O, different tools in H2O, so Java's AI or sparkling water and other stuff on our first day. And the second day, we have some tech talks and the panels and all that stuff. So you can also see all of the H2O Grandmaster, the Cargo Grandmaster in one place on the second day. So here is gift to you guys. So if you want to come and join us, please use this code here. Oh, this is not really practical for now, but hope that you can see that from the poster. So it's a Paris WiMLDS 50. So this code here will get you the free ticket to both days if you wish to travel to London at the end of October. So please come to join us if you want. That's it from me. Thank you.
Thank you so much. Any questions for Joe Fry?
Yeah, the problem of baseball player performance prediction seems to boils down to time series modeling, forecasting. So have you tried to use autoregressive moving average models of time series?
No. So the point was to demonstrate how H2O, IBM, and agility tools work together. So this is actually like a side effect that I didn't expect to happen. So. But yeah, I see your point. If you want to treat it into a more proper time series problem, I may use other algorithms, maybe deep learning as well. But the point is that at the time, I only think about how to do a simple regressions to make something happen, so that to make some predictions. I didn't care too much about the how it will be used. Yeah, but it seems to be okay. I wouldn't say they're like world-class predictions, but it seems to be okay for Ari to differentiate different baseball player, different player that he wants to look at times. So I guess the outcome, the actual outcome, whether they are super accurate or not, it doesn't really matter in this case. It's about how you find out the best player.
Classify the players.
Yeah, from the group and get them before people get into them and sign them up.
Okay, thank you.
I have a question for you. We had one of the creators of Lime on the Paris Machine Learning meetup, actually. When he came out, he was still doing his thesis and trying to finish up and everything. I'm kind of surprised about 15 months down the road from the talk he actually gave back in January of 17, that it has actually gone down to be so well used. And I'm kind of triggered by what you were saying. That is, somebody that is kind of knowledgeable in the domain gets to actually get it much faster, even though he knows all the statistics and everything, by getting the Lime layer on top of it. Do you have any other comments on this? Or, I mean, it's not really a question, but I'm kind of surprised by the whole thing, by how much it took, I mean, 15 months is not a long time, and it gets to be used, and it gets to be very used, as in people interpret these things. So any other insights that you're getting out of using Lime?
I think it just shows how bad we were before we have some tools like Lime before. So we data scientists sometimes we care about the metrics. It could be AUC, it could be women's square. We use that as a holy grail to explain to people, this is how good the model is. Look at this number, it's like perfect. But then we don't realize that some people don't care about the metric. They care about the actual insight from the data from the model. So in order to ask them to trust you, to gain the trust from people without machine learning experience, you need to bridge the gap with some approximate reasoning. So Lime is one of the tools that we invested in. So we have looked at different contributions from input. That is only one way to look at the problem, I guess. But that in itself is better than just give them a number, like this is AUC, 0.9 something. This is, go home with this. With that, if you gain a trust with them and then you can work together, people's minds is super clever. When you show them visualizations like this, they can quickly relate to more insight without doing more machine learning problems, because they have the knowledge. So Ari has been doing this for 30 years. He knows what's going on with different attributes. He knows how different players should behave in different age. So this gives him the confidence that he needs to step forward and try to use this as a base to validate his thinking for the player. But again, I think this we can apply to many other industries. So in medical, in other things, if you want to gain the trust, you need to do something like this to bridge the gap. So this is not perfect. By all means, this is not the perfect answer to answer what's happening with the machine learning model. It's too, sometimes it's just stochastic. Is it too linear, too localized? But if you don't have this to back you up, you will never gain the trust with the stakeholder or the decision makers, and they will never use your model in anger. But I think this is one of the good examples saying you can kind of put them together. But this is only the beginning, I guess. There will be more that needs to come to explain model, to gain more trust from the people that don't know about machine learning.
So do you intend to put an AutoML layer on top of this? I mean, there is an explanation thing that goes in there. I guess it's too far away.
Yeah, I think it's too far. But maybe at some point we can automate a bit more. So I guess we just want to automate the task so people can have more time to think about the business problem and how to communicate it. This is like telling a story with the tools rather than doing it like a cargo competition. So explaining the problem is more important than the actual result.
Okay. Any other questions for Joe Fine? Okay. Well, thank you very much. Caroline, c'est à toi.
We have a tradition, which is taking a picture at the end of every meetup. So I'm also going to give you one very important information. On your left, which is my right, there will be food and drinks if you want to network together. So now I'm going to ask Erin, Chiara, Joe, Akin, we're going to take a picture.
Voilà.
Yeah.
This way.
Yeah, I'm taking a video actually.
All right.
Thank you.
You can say it. Are we done?
Thank you.
All right. Thank you again for coming. Donc le prochain meet-up pour vous c'est
Mercredi prochain.
OK, et pour nous ce sera le 10 octobre. Merci encore d'être venu et puis voilà, on va essayer de boire quelque chose.